Hello, today we will discuss the power consumed by a resistor. Here we have a resistance and the AC source. The AC source is represented, its instantaneous voltage V is equal to V naught sine omega t. The instantaneous current across the appliance R, we already calculated it. It is equal to I naught sine omega t. Here the voltage and the current are in same phase. It means the phase difference between them is zero. And we know the average power is equal to Vrms into Irms into cos phi. P average is equal to Vrms, Irms into cos phi. As phi is equal to zero, so we are putting the value of phi as zero. So we will have P average is equal to Vrms into Irms as cos phi is equal to 1. But we also know Vrms is equal to V naught by root 2 and Irms is equal to I naught by root 2. So by plugging these values, we will have V naught I naught by 2. It means P average is equal to V naught by 2. Using Ohm's law, I naught is equal to V naught by R. So we will have it is V naught square by 2R, or it is equal to half I naught square R. If we use the time graph between voltage, current, then voltage is represented by this blue line and current is represented by the red line. So the power comes as this, and it is in positive cycle. So the positive power is always absorbed by the appliance. Hence, the resistance dissipate power in form of heat, and it is equal to I naught square R by 2. Now next, if we find out the the inductor circuit first. In case of power consumption in inductor, here we use the appliance inductor and the source voltage is V, and V is equal to V naught sine omega t. Now, using the Faraday law of electromagnetic induction, the effective EMF is equal to minus L di by dt across the inductor. By this equation, we already find out the I is equal to I naught sine omega t minus pi by 2. So in case of pure inductor, the current is lagged behind by pi by 2 degree. It means voltage is leading by current by pi by 2. So the power factor comes out cos phi is equal to cos minus pi by 2. Hence, again using the equation, P average is equal to Vrms, Irms, cos phi. We will put the value of cos phi and it comes cos minus pi by 2. So the power dissipation across the inductor is Vrms, Irms, cos minus pi by 2 or Vrms, Irms into 0. At cos minus pi by 2 is 0. So the average power dissipation across the inductor is 0. Now if we discuss the time graph for voltage is the blue one and the current graph or the time scale it is red one. So if we draw the power graph for pure inductor, it will comes like this. It will have two positive lobes which are absorbing the power and two negative lobes for a cycle which are releasing the power to the source. So power released to the source is equal to the power absorbed by the inductor. Hence net power dissipation or consumption by the pure inductor on an AC circuit is 0. Now next appliance is the capacitor appliance. Here we are using again the source voltage V is equal to V naught sine omega t and the current equations we know I is equal to I naught sine omega t plus pi by 2. So here the angle between V and I is pi by 2 and current is leading by pi by 2 than the voltage. So voltage is lagging behind by pi by 2 in pure capacitive circuit. So phi comes out how much? Pi by 2. And we have power equation. The average power is equal to Vrms IRMS cos phi, and cos phi is cos pi by 2, and cos pi by 2 having value 0. So we again get the average power consumed by capacitor in AC circuit is 0. During charging and discharging of the capacitor, there is no dissipation of power in AC. So we may again consider the time graph. We will have the current as red, voltage as blue graph, and power, which we will get, will again have positive and negative lobes regularly. So power is absorbed on positive lobe, and here power is released to the source by the capacitor. So net power consumption becomes zero in every cycle. Thank you. We will